Welcome everybody. So today we are going to talk about section 6.3, but before we do that, we're going to look at the exam. I'm going to review the exam with you. You should be able to access your results on the exam by going into My Open Math and going through the grade book. You can also find the exam in the Exam 3 review section of My Open Math. You can also find Exam 2 in the Exam 2 review section, and it'll even show you the answers, so you can look at the correct answers to your responses there, okay? So I'm going to take you over to my browser and just show you how that works. I've logged in with a fake student account, so I should be seeing what you'll be seeing, so we can look at that together, okay? So here we go. Looks like I was already logged in here. So should be seeing my browser, and so let me just zoom in a little bit to make it easier to see. Okay, so you can see we've got at the very top of the page we have Exam 1 to review, Exam 2 review, and Exam 3 review. If you click on Exam 3 review, you'll see the Exam 3 sitting right here. You can't take it anymore. Even says this assessment is in review mode, no scores will be saved. All right, but you feel free to open it up and look at it. Go in here, you can look through all the problems, and you can even have it show you the answer. Now on these problems with these integrals, showing, if you click show answer, it just tells you to check the detailed solution. So click this detailed solution and it'll show you the correct response here. All right. I keyed in these solutions late last night. I hope I did them right. I think they're all correct, but I did it quickly. So, you know, if you see something wrong with those, feel free to email me if it doesn't look quite right. But you can actually check it just by plugging these things in up here. And I tried to do that, but I don't know if I was able to do that with every one. But so you can go through each problem, and you can check the solutions here. All right. Note that some of these have three-dimensional images. You can feel free to rotate those around and look at those. Some of these images, I couldn't get them to fit on the screen as nicely as I wanted to. If you're on a PC, I don't know what the keys are on a Mac, but if you're on the PC and you hold down if you click on the 3D image and then you hold down the Alt button and use the arrows, you can move it around a little bit. All right, so if you want to get a better look at it, you can, by holding down Alt and the arrows, you can move it around. There's some other keyboard commands. This is from CalcPlot 3D, so if you just Google CalcPlot 3D keyboard commands, it'll give you a list of those. All right. On Mac, I would expect that it would be Option and arrows, because usually Option does what Alt does on for a Mac, versus a PC. But I haven't tried it on a Mac, so I'm not sure. The questions that you see here will not be appearing in the same order that the questions appeared on your exam, because I had it shuffle the question order, all right, except for the very first question. So it may or may not. Since it's you looking at it, maybe it will be in the same order that you saw. But the order that I'm going through here probably will not match the order that the questions were on your exam, okay? So if you ask me to look at a question, please don't ask me to look at problem number 6, because I don't know which problem number 6 was for you. Please refer to the type of the problem. You can also just go in here and click message instructor about this problem. I should put the link in to put this to the forum as well. I'll put that link in after class. That would be even better if you post it to the forum. That way I can respond to everybody. You should always do that if you can. And I think this is one that we had a question about. So somebody asked the question, how do you do this one? All right. So here we have an integral over a parallelogram. Now that's kind of a messy technical integral to set up. You got to split it up into pieces unless you change variables, all right? And you can change variables to turn a parallelogram into a rectangle. And that was the idea here. And I gave you the change of variables that's recommended. Okay, so for my problem, everyone's problem looks a little bit differently, but for mine, I'm going to copy this down and we'll go to the paper and we'll take a look at this one. Let me just write down the change of variables as well. Okay. So let's, let me write down the vertices here. The vertices were those might come in handy. Okay, so let's go down to the paper. So here we have it. We want to do this integral. We're going to do a change of variables. Okay, so what we need to do is we need to solve these for x and y, because we're going to need to substitute those in for x and y over here. Okay, so just start solving these by, I would multiply this one both sides by 18. Okay, so if I multiply both sides by 18, I get 18u equals 2x minus 4y. And this equation, to solve this for v, I would multiply both sides also by 18. So I'd get 18v equals negative y. Oh, let's write it in the x and y order. So we'll do 5x minus y. Okay. Looks like my video, my internet's getting a little bit choppy the last couple of days. I don't know why. I'm right next to my router, so it shouldn't be a problem, but that's nothing I can do about it. I'm plugged in via the Ethernet cable, so this is as good as it's going to get. I hope it keeps working okay. All right, so we need to solve this for x and y. Well, one thing I can see, one thing you can do is just solve one equation for y and then plug it into the other equation and solve that for x and you'll get it. But there's a kind of a slicker way to do it, and it's called the elimination method, where you just you multiply the equations by a number and then you add them together and try to get one of the variables to cancel. All right, so for instance, if I multiply the second equation by -4, I get this. What's -4 times 18? It's 72. -72, I believe. So if we multiply that second equation by -4, we get this. All right, let me write the top equation over again. If I now add the equations together, the y's will cancel. All right, so let's see, 72 minus 18 is 54, so that's going to be -54. Oh, these are not like terms. Sorry, can't add those. 18u minus 72v. The y's cancel, but I do get -18x. All right, divide through both sides by 18, and we've solved for x. Right, -18, we've solved for x. So I'm seeing that x is u minus, or rather it's -u plus, because I'm dividing by negative, 72 divided by 18. Let me just do that quickly to make sure I get it right. 4. And I've rigged these so that they should all come out to whole numbers on all your problems. I don't think any fraction should appear here. Okay, so that's x. And then we can try to do y. To get y, instead of multiplying the bottom equation by -4, I might multiply the bottom equation by -2, and the top equation by 5. All right, so let's multiply the top equation by 5 and write it down. So 5 times 18, that's 90. And then the bottom equation by -2. All right. And now I can add these equations together. All right. So 90 minus 36 is 6. Oh, I'm doing it again. These are not like terms. One's a u, one's a v. Don't do that. 90u minus 36v. Negative 20 plus 2 is negative 18. Okay. Divide both sides by negative 18. What's 90 divided by, oh, we know what that is. That was just, 90 divided by negative 18 is negative 5, right? So I'm getting negative 5u plus 2v. Okay. Let me know if I make a mistake. I'm prone to make mistakes when I'm twisting my arms to get below the camera here. There's too much going on for me, so I get a little distracted. All right, but this looks good. So now that we have x and y, we can substitute those in up here. But before we do that, let's compute the Jacobian, okay? To save space, I'm going to do that over here. The Jacobian is, what we do is we take the, what was it, xu times yv minus xv times yu, and we take the absolute value of that, right? So xu is negative 1, yv is 2. So I have negative, oh, wait, negative 1 times 2, yeah, negative 2. And then xv is 4, yu is negative 5. So 4 times negative 5 is negative 20. So the Jacobian here is just absolute value of 18 is 18. So when you make the change of variables from xy to uv, you've got to multiply by the Jacobian. And what that's doing is it's accounting for the fact that areas are getting distorted. When we change variables, you know, a 1 by 1 rectangle in the xy coordinates does not have area 1 in the uv coordinates, right? It got skewed and became a parallelogram. And so the areas have been distorted a little bit. And so this compensates for that distortion. It's telling, this is the factor by how much the areas were distorted, and so we have to multiply by this. Well, 1 over this is the factor by how much they were distorted, so we multiply by this to undo that. All right, so we go back up here. We're going to plug in this for x and this for y, and we'll simplify it. Okay. So 5 times x, we're going to have 5 times negative u plus 4v, and 3 times y, that's negative 5u plus 2v. And we have to multiply by the Jacobian, right? And then we are going to do either dx dy or dy dx. In this case, the parallelogram is turning into a rectangle, so it's not going to matter. We can just do dx dy, let's say. Oh, sorry, it was dx dy, it's du dv. Oh boy. Okay, we've just changed from dx dy to du dv. All right, so let's simplify what's in here. We have negative 5u minus 15u, that's negative 20u. We have 20v plus 6v, that's 26v. You know what? Let's take that 18, pull it outside. Let's do that last. It's a constant, so you can just pull it out front of the integral. You know, why make these numbers bigger than they have to be? In fact, there's some other numbers we can pull out. We can divide everything by 2 here, pull that out. Let's just make this integral as easy as possible to do here. Dividing everything by just pulling the 2 out, factoring out, and pulling it out front. I'm getting negative 10u plus 13v. du dv. Okay, so I made that integral as simple as I could. Now, what are these bounds? All right. Well, for these bounds, what we have to do is we have to go look at the picture. So let's go back to the picture. This blue line on the left, all right, what is the equation of that line? If you look at it, it has slope 5, so and it has y-intercept 0, so it's the line y equals 5x, right? So if y equals 5x, then y minus 5x equals 0. Now, if you look at the equations for u and v, you see that that makes v equal to 0. So this blue line here on the left is just v equals 0. Same thing, all right? What about the blue line over here? Well, if this was v equals 0, this is probably v equals some other constant, right? And sure enough, it is. What constant would it be? Let's see. If it goes through the point 4, 2 here, right? So x is 4, y is 2. So just plug those in here. So I'm plugging in 2 for y, -2 plus 4 for x is 20. So I get 18 divided by 18. That's v equals 1. So this line corresponds to v equals 1. So we're going from v equals 0 to v equals 1. All right? So I just made a note of that. Now let's look at these red lines. This red line here, this is a line with y-intercept 0 and slope 1/2, right? So this is just y equals 1/2 x, right? Now that corresponds to setting, that's the same thing as saying 2x minus 4y equals 0. So that line, this red line here, corresponds to u equals 0. So I'm going to make note of that. And this other red line must be u equals some other number. What other number would it be? We'll just find a point on this line, like, oh, here's a nice one, 9, 0. So just plug in 9, 0 up here, and you see that that makes this u equals 1. Okay? So we're going from v from 0 to 1 and u from 0 to 1. Okay, so let's go back. That gives us our bounds here. Okay. And I'm gonna leave it there because I think from here you know what to do, right? We just anti-differentiate and evaluate, right? I think we did the complicated part here. Okay, so that's as far as I'm going to go. I hope that was helpful. Let's go back to the exam. Where did it go? All right, I was in my Firefox here. Okay. So back to the exam. Let's proceed along here. One of these was converting from spherical to rectangular. That one's not too bad. Another one here, if you use your scroll wheel on the mouse, or if you're on an iPad or tablet, you can zoom out on these. Right? This is the finding the volume between these two spheres here. Right? I'll let you look at that one yourself. The answers are given below. The volume of the solid lying under the plane. Right? Well, here's a picture of the plane. Now you can tell what the x and y bounds are just by looking at the picture here. They're given in this format up here. This is the first interval is an interval for x, and then cross an interval for y. That's the notation that they're using. Okay, so this says that x ranges from -3 to 3, and y ranges from -4 to 4. That's how you read this notation. But you don't even need to know this notation if you just look at the picture. You can tell, here's the x-axis. It goes from -3 to 3. Y is going from -4 to 4. All right, so those are going to be the bounds that you put here. All right, and to find the volume of a solid under a graph, well, you write this graph as a function of x, y, and you put it in here. All right, so that's how you do that one. This one, this one. Okay, this one I want to talk about. There was a little problem with the the coding here, and so it wasn't accepting all the correct answers. And sorry about that, and I really appreciate you guys being the guinea pigs as we, put this stuff together for the very first time. I've never done testing online before, so you guys are the guinea pigs for testing all these things out. And but fortunately, you were able to show your work for this. So I looked through your work, and even if you put the wrong answer, even if you got marked wrong here, if your work was correct, I gave you full points, okay? It is showing the correct answer now, though, okay? So if you look at it now, it'll show you the correct answer. Moving on here, let's just look at this, a triple integral for this tetrahedron type shape. I'll let you look at the answer there and see if you can sort that one out. Here we have a flower. These nice polar plots are really nice. They make these nice flower pictures here. There was a homework problem like this, so I'll let you look at the solution and figure that one out. If you have questions, let me know. And then converting points to cylindrical coordinates. All right. So like I said, if you have questions about these, just let me know. I also want to point out that if you just go to the grade book here, it'll show you your grades on all of these assignments. All right. I'm a fake student. I haven't done any. This fake student hasn't done many assignments. So you'll notice some assignments have a little D next to them. That means that grade has been dropped. All right. I have dropped the lowest exam grade. That will include all exams except the final exam. So only among exam 1, 2, and 3, the lowest of those will be dropped, and it will have already been dropped. All right. Final exam will not be dropped under any circumstances. There's a summary of your work. Remember, always look at the past due column. Don't look at the past due and available, because it doesn't make sense to grade things that haven't been due yet. So just look at the past due column for your grades here. Okay, so you should be able to look through here. Also look at the feedback, all right? Next to your exams, I gave feedback. This is very important because when you showed work, I wrote a comment if there were any issues with it, all right? So make sure that you look through here. I'm not sure if, I'm not sure what happens if you click this number. Maybe it'll show you every question. Let's see if it shows my feedback here. I don't know. I was hoping I'd see my feedback right next to the problem. I'm not seeing it here. Well, you may have to look at the feedback and then go reference the problem separately. Okay. But be sure to check out the feedback, because I did leave feedback on some people's exams. Okay. All right, let's get out of the screen share here. So any questions? Okay, I'm not seeing anything, so I'll keep my eye out. It's hard for me to see the chat when I go to share my screen, but when I switch, I'll keep an eye out for messages. Okay, I just want to talk about, we're going to move on and talk about some new material today. And I'm going to try to finish up the material today so that we have next week for a review. If we're not, we may have just a very little to do next week. So what we were talking about so far was vector fields. And so this is a way of a vector field is just assigning a vector to every point in space. And these things can be used to model fluid flow, wind, electromagnetism, gravity. Whenever you're feeling a force exerted on you at any point in space, that can be viewed as a vector field because the force has a magnitude and a direction. But you can also view it as representing velocities of particles or just the motion of a fluid or something like this. So we talked about vector fields last time. And we also talked about line integrals. So we talked about how to integrate through a vector field. And that's very important because you might want to know as like a sailboat goes through the water, what does it experience as far as the currents of the water? The currents of the water that's flowing through can be represented as a two-dimensional vector field on the surface of the water, where the vector represents the velocity of the water at any point. And so you might know, you might want to know, like, what does that boat experience as it goes through the water? And so and to do that, we integrate along the path of the boat through the water, and we account for the vector, the force vector at every point along that path. And when NASA launches things, they want to do this to know the effects of gravity and things when they get into orbit, and that gravity has a different force depending on how far you are from the Earth, and so these things need to be accounted for. And then the path that they send these things out to go orbit other planets, it's not a straight line, so it's not trivial how the gravity is changing as it moves along. So you want to be able to integrate along these vector fields. So we did that. We did line integrals. So today what we're going to do is we're going to talk a little bit more about line integrals. In particular, in section 6.3, we're going to talk about line integrals when we're dealing with conservative vector fields. And we talked about a conservative vector field as a vector field that happens to be the gradient of some function. All right, so you have a function, you take its gradient, you get a vector. Well, you can take the gradient at every point, and so you get a vector field. Some vector fields are gradients of functions, and those we call conservative vector fields. Some are not gradients of functions, and so they're not conservative vector fields. So conservative is this important thing, and we're going to see why it's so important today. And then we're going to talk about Green's theorem. Green's theorem is a very important theorem. It's an extension of the fundamental theorem of calculus. And so we'll talk about that. So let's go down, and I want to actually review a line integral problem, okay? And then we'll revisit that problem later on when we start talking about Green's theorem, and we'll see another way to do it, all right? But I want to show you how to do this line integral problem, and I think it'll be useful for you because there's a line integral problem just like this on the homework involving flux. We're not going to do flux here. We're just going to do a normal line integral, but you can apply the same strategy for how you have to do that homework problem with flux, okay? So let's go down to the paper. And here is the line integral that we want to do. We want to compute the integral along a curve of f dot dr to a vector field. And when I dot it with dr, that means I'm integrating along a curve given by r of t, all right? And I have to tell you what the vector field is and what the curve is, okay? Where f is the vector field, 2xy, comma, y minus 1, okay? And C is going to be a rectangle. And this is where it's similar to the problem involving flux. All right, so we're going to learn how to deal with a rectangle here. And C is the rectangle with vertices, plural for vertex, 0, negative 1, 1, negative 1, 1, 2, and 0, 2. Oh, and I'm not done. I have to tell you the orientation of this curve. Which direction are we going around this rectangle? Clockwise or counterclockwise? So let's say oriented counterclockwise. The usual orientation of mathematics. We like to do everything counterclockwise. All right, so let's just draw a picture. So 0, negative 1, that's this point over here. 1, negative 1. 1, 2. And 0, 2. So this is our rectangle. And now we're going along it counterclockwise. So let me put these little arrows in here to specify that. Okay. So we're integrating around this rectangle. Now let me show you a picture of this vector field so we can get an idea of what's going on here. All right. So if I go down on our page and click the CalcPlot3D link, it'll take us to CalcPlot3D. All right, so we don't need this graph. What I'm going to do is put our vector field in here. Feel free to do this if you're working on homework problems. It can be useful to get a picture of what's going on here. 2xy was the x coordinate. Y minus 1 is the y coordinate. Oh, yikes. Just knocked something off my desk. Didn't need that anyway. And this is going to be a two-dimensional vector field, so let's just hit restrict to 2D. No need to see the third dimension here. And let's plot it. All right, some of these vectors are pretty long. They're already scaled down by a factor 4, notice. It says scale vectors by dividing by 4. If I don't divide by 4, this is what it looks like. It looks like a mess, right? So that's why it's dividing. In fact, we should probably make it divided by even a larger number just to get a better picture of what's going on, right? But realize these vectors are actually 8 times as long, okay? But when I scale them down, I get a kind of a cleaner picture. So what we're doing is we're coming around this rectangle, down along the y-axis, down below the, only to here, along the x-axis, coming back up and back. So we're going along that rectangle there, okay? We're integrating along this rectangle. So I just wanted to show you that so you can get a picture of what we're dealing with here. And what is happening is as we move along this rectangle, we encounter different force vectors, right? Like for instance, the force vector, let me try to get an accurate, the force vector up here is pointing this way. Okay, so what I'm doing at every point is I'm taking the dot product of my tangent vector with the force vector. That's what f dot dr is doing. I'm dotting the force vector with my direction vector. So you can see here they're pointing in opposite directions. So I'm getting a negative result. If they're pointing in roughly the same direction, I get a positive result. If they're orthogonal to each other, I get 0 as an answer. So depending on where I am, what direction I'm going, and which direction the force vector is pointing, I'm getting a different number. And I'm just integrating those numbers along here and just kind of basically just adding, an integral is kind of like just adding up all those numbers. So we're finding the total influence that that vector field has in the direction of our motion. If more often than not it's pointing against our direction of our motion, then we're going to get a negative answer. If more often than not it's pointing in the direction of our motion, it's going to give us a positive answer. Let's actually go back to the picture and to make a guess. What answer are we going to get here? I'm going along this rectangle here. As I go around counterclockwise, are the vectors more often pointing in the direction of my motion or against the direction of my motion? And you have to account for the size of the vector too. The bigger the vector, the more influence it has. So make a guess. You know, am I going to get a positive answer here, negative answer? Maybe you think they balance out. Maybe you think they get 0. Right? So just something to think about. Okay. Back to the sheet. Okay. So to do a problem with rectangles, well, we have these corners. It's not a nice smooth curve, which means we need to break it up into pieces. So I'm going to do that. I'm going to call this R1, this R2, R3, and R4. So I have 4 separate curves I'm going to integrate along. And this is what you'll have to do with the flux problem on the homework. Break it up into 4 different pieces. There's 2 flux problems, so only one of them. So now we have to parameterize each curve. Okay? So how do we parameterize? Let's start with R1. Oh, actually, let me point out what we're going to do, just to give you a big picture idea. What we're going to do is we're going to take this integral, and we're going to break it up into pieces, right? We're going to first integrate along, you know, the first curve, R1, let's say that parameterizes C1, right? And then we're going to integrate along C2, and then C3, and then C4. Okay, so I could have labeled these C1, C2, C3, C4. There's just, I drew my picture too small and there's no room left. So I'm not going to do that. And I also should be writing this integrand each time. So I'm being sloppy. I'm just sketching out the main ideas. We're just breaking it up into pieces. So what we're going to do first is we're going to work on this first integral. Okay, so we need to parameterize R1. Okay, so R1 goes from this point to this point. Its y-coordinate stays the same. So I know that when I parameterize R1, that the y-coordinate is always equal to -1. Don't have to worry about that. Now the x-coordinate goes from 0 to 1. So how about just I put a t here? Okay, so what's happening is t goes from 0 to 1. And that will, when t is 0, it's going to put me at this point. And when t is 1, it's going to put me at this point. So that parameterizes that curve. Now, to do this integral here, we need to find dr. Now remember, dr is r prime of t dt. All right, so we need to find, this is going to be dr1. So this is going to be r1 prime of t dt. So we're going to find r1 prime of t. Okay? So, well, that's very simple. I just differentiate this vector, and I get 1, 0. Okay. So when I do this integral over the first curve, I'm going to evaluate my vector field here, and then dot it with this, dt. Okay, so let's write that down. I'm going to take my vector field evaluated on this curve. So I'm plugging in t for x and -1 for y. Right? So I'm going to get -2t, comma, -2. Just plugging this stuff into here. That's f on my vector field. Okay. Then I'm going to dot it with dr. dr is r prime of t dt. So r prime is this. So I'm going to dot it with 1, 0 dt. And what does t range from? It goes from 0 to 1. Okay. So let's see what I get here. Well, the dot product just becomes -2t. Right? And that's just -t squared evaluated from 0 to 1 when I anti-differentiate. And so the answer here is -1. So what we're saying is overall, we're experiencing a negative influence of force on that curve. In other words, the force is pointing more in the opposite direction of our motion than the direction of our motion. Okay. Now let's do R2. So this was C1, all right? For C2, we need to compute R2. We have to parameterize R2, okay? So R2 of t, let's see, it starts here and ends here. So the x-coordinate stays the same. It's always equal to 1. The y-coordinate starts at -1, and then it increases until we get to 2. So how much did I have to add to get from here to here? It was 3. So just put a 3t here. That will work. All right, where t goes from 0 to 1. When t is 0, just check. We're at 1, -1. Right? When t is 0, that's gone. And when t is 1, we're at 1, 2. So I have successfully parameterized this line segment. Okay. We need to find r prime. Now maybe to save space here, maybe I'll do that. Well, no, we'll do it right here. R2 prime of t. is 0, 3. So now I can plug this stuff in, right? So I'm going to plug these things into my function, okay? So my vector field was 2xy was the first component. So I have to take 2 times this times this. So that's going to be -2 plus 6t. And then the second component was y minus 1, right? I'm just looking at my vector field here. 2xy was the first component, y minus 1 is my second component, right? So this is 2 times x times y, and then y minus 1. So it's going to be -2 plus 3t. And I'm going to dot this with the r prime of t. So that's 0, 3 dt. Okay, and I'm integrating from 0 to 1. Okay, when I dot this, I get -6 plus 9t dt. And the antiderivative is -6t plus 9/2 t squared, evaluated from 0 to 1. All right, well, -6 is -12/2 plus 9/2. That's -3/2. Okay. Again, a negative influence more so than any positive going up this direction. So overall, we had a negative influence of the force vector. Right? So more often than not, it was pointing against our motion. Okay. So let's keep going. I'm gonna just check the chat. No questions yet. Okay. Feel free to send a question if you got one. Okay. We have to do C3 and C4. Okay. So for C3 here. I'm going to use R3 of t. Okay. Well, take a look at the picture. R3 starts at 1, 2 and ends at 0, 2. Starts at 1, 2, ends at 0, 2. So the y coordinate stays the same. So that's just going to be 2 the whole way. The x coordinate has to start at 1 and end at 0. So why don't we just do 1 minus t? Okay. So there we go. And that is true from 0 to 1. When t is 0, we're at 1, 2. When t is 1, we're at 0, 2. Okay. Compute the derivative. -1, 0. Okay. Plug these in to our function. Right. Here's our function. So we have to do 2xy. So 2 times this, right? So it's going to be 4 minus 4t. And then y minus 1, so just 2 minus 1. And we're going to dot that with r prime. And we're going from 0 to 1 again. All righty. So that becomes the integral of 4t minus 4. Right? And anti-differentiating, we get 2t squared minus 4t, evaluated from 0 to 1. And that gives us -2. Again, looks like our integral is we're going mostly against the force vector here. We keep getting negatives. Okay, and then finally C4. We do R4 of t. Now, for this one, it starts at 0, 2 and ends at 0, -1. So the x-coordinate stays 0 the whole time. But the y-coordinate looks like it starts at 2, and then I'm going to be subtracting 3t. So this is from 0 to 1. When t is 0, we have 0, 2. When t is 1, we have 0, -1. So that looks right. R4 prime of t equals 0, -3. So we plug these into our force vector field. All right, so our force vector field was 2xy. So I'm going to take 2 times this times this. Well, that's 0. And then y minus 1. So this minus 1. So that's 1 minus 3t. And I'm dotting that with r prime dt. Oh no, I thought it was off the screen. I'm good. Okay. So many things to look at over here in control center. In the control center here. All right, so dot product these, you get -3 plus 9t dt. Anti-differentiate, we get -3t plus 9/2 t squared evaluated from 0 to 1. What do we get? -3 is the same thing as -6/2 plus 9/2. Right? So, oh, we finally got a positive integral. Great. I felt like that had to happen at least once, right? It would be weird if the force was pointing against us the whole way. It can happen, but it seems like it would have to be a very special force field. Okay, so remember what we said we were doing. We were going to add all these up, right? Because that gets us all the way around. So that's all we got to do is add up our integrals. So let's see what we got. First, we got -1 for the first one. Then we got -3/2 down here. Then we got -2. And then we got 3/2. Okay, well, those will cancel. The total is -3. So we did it. F dot dr is -3. Right? And so sometimes this is how you have to do it. If the region is not a nice smooth curve, if you can't parameterize it as one, in terms of one parameterization, break it up into several parameterizations and do it in pieces. Okay? So those of you who guessed negative, gold star for you. Good job. All right. All right, that's line integrals. Now we're going to find out a much easier way to do a problem like this. Okay, and that's going to be Green's theorem. So we're going to come to that, and you'll see it. It makes it so easy. It's amazing. All right, but that's how you do it as a line integral. So to work our way up to Green's theorem so that we can have that nice, easy way of doing things, we're going to enter section 6.3. Now, in section 6.3 and 6.4, I am picking and choosing topics here because I want to get through the main stuff. So you will see things discussed in the textbook that we are not going to go over, okay? Because I want to get to Green's theorem, and I want to keep things simple. But there's a lot of interesting stuff that I am breezing over, okay? So keep that in mind. You may want to read through the book and check that stuff out. So what we're going to do in this section is mainly we're going to get to this thing called the fundamental theorem for line integrals. We have the fundamental theorem for calculus. That's in Calc 1. Well, now we have a fundamental theorem for this kind of integral. So yeah, the fundamental theorem of calculus, just let's review that. Fundamental theorem of calculus says that there were two formulations of it, but one of them says that if you want to do the integral from a to b of a function, f of t dt, that the way you can do this integral, which is really just adding up a bunch of little rectangles underneath the graph of the function and finding the area under the function. Well, it says this very, very amazing thing, this very, very amazing fact that we use all the time in calculus. It says that you can evaluate this just by taking the difference of two values. Right? And what is this capital F? Where capital F is the antiderivative of little f. I shouldn't say the antiderivative, it's an antiderivative. You can use any antiderivative. So any antiderivative of f. And that's amazing. The fact that this whole like summing process of adding up these areas, these little rectangles, getting the area under the curve, ends up being as easy as just finding an antiderivative and taking the difference of its values. That's spectacular. It's amazing. And we reuse this whenever we do integrals. This is how we do integrals, right? We try to find that antiderivative. That's how we were doing the integrals in the last problem we just worked on. And that's the fundamental theorem of calculus. So we have a fundamental theorem for line integrals too, okay? But first, let me remind you some things about some of the terminology we had. Notice the section is called conservative vector fields. Okay, what does it mean for a vector field to be conservative? It means that it's the gradient of some function. Okay, so a vector field f is conservative if it is the gradient of some function f. So in other words, capital F is the gradient of little f. Just writing it mathematically. That's what it means to be conservative. Okay. Not every vector field is conservative. All right. And if you want to get if you just take a function and take its gradient, you get a vector field, and you're automatically going to get a conservative one. Now, let's go ahead and write down the fundamental theorem for line integrals. Fundamental theorem for line integrals says the following. It says that if you take the integral over a curve of the gradient of a function dotted with dr, so this is a line integral. We have a vector field, and we're dotting it with dr, then that is equal to f of r of b minus f of r of a. What is r? R is the parameterization of this curve, right? So we came up with an r in the last problem where we found a set of 4 r's that parameterize that rectangle. That's what r is. Notice it looks just like the fundamental theorem of calculus. And look what we did. If you have the gradient in here, you undo the gradient. You find the function whose gradient was this vector field, and you evaluate it here and here. Same thing we did here. See, capital F is the function whose derivative, think gradient, so derivative is a one-dimensional gradient, that gives you this, right? So it's a little weird. I use the capital F here and a lowercase f here. That's how the book does it. I use the same notation. Hope that's not confusing. But yeah, this little f is playing the role of the capital F here. Okay. And this is just the derivative of this. So that means that this is kind of like the antiderivative of that, but related by gradient, not just derivative, but by gradient. Okay. So this is fantastic. This means that if we ever want to do a line integral, if the vector field that we're dealing with is the gradient of a function, all we have to do is find that function and then evaluate it at 2 different numbers, and we're done. At 2 different points, I should say, and we're done. That is fantastic. That'll make our lives so much easier, all right? So let's do an example. All right, so let's take our vector field is going to be x comma negative y. Okay, and we want to compute, the integral along c of f dot dr, where c is the line segment from 0, 0 to 3, 4. Oh, sorry, I went off the screen there. Okay, so here we have a vector field. We want to compute a line integral along this line segment. Okay, let me show you how we would do it before we knew about the fundamental theorem for line integrals. Before we knew about the fundamental theorem of line integrals, so approach 1, what we're going to do is we are going to parameterize this curve. Right? So let's define r of t to be, we need to find a curve, we need to parameterize this line segment. So how about this? How about 3t comma 4t, where t goes from 0 to 1. I like to parameterize from 0 to 1. It just seems like the easiest way to do it. Don't have to do it that way, but that seems like a nice way to do it. So when t is 0, we're at the point 0, 0. When t is 1, we're at the point 3, 4. Okay? And then we would find r prime of t. So this is 3 comma 4. And then we would do what we were doing before, where we're going to take the r of t and plug it into f. So it's going to be 3t comma negative 4t. Oops. Sorry, I scrunched that in there. That's a negative 4t with an angle bracket next to it. All right, and then I'm going to dot that with r prime, 3 comma 4. I think I did that wrong. No? Wait, is that all right? No, that's fine. That's fine. And I'm going to do dt, and I'm going to go from 0 to 1. All right, so let's do this dot product. So that is 9t minus 16t when I take the dot product. So that is negative 7t dt. All right, 9t minus 16t, yeah. And the antiderivative here is, oh, I'm taking the antiderivative, don't do the integral anymore. Negative 7 halves t squared from 0 to 1. So it's negative 7 halves. All right. Got the answer. That's the old-fashioned way. That's not using the fundamental theorem of line integrals. That's how we would do it, from what we knew from last couple lectures, right? Let's see how the fundamental theorem for line integrals would get us the answer, okay? So let's just let's do approach 2. Okay, the fundamental theorem says that if this is the gradient of some function little f, all I have to do is evaluate that little function, little f, at the endpoints of my parameterization. All right, the endpoints of my line segment. So can I find this little f? Can I find a function whose gradient is this? And yeah, that's not hard to do at all. So just with a little bit of inspection here, you can see that little f would be 1/2 x squared minus 1/2 y squared. Right? That satisfies the fact that its gradient is equal to f. If I just take the gradient of this, I get this. Okay? So we found little f, right? So all we have to do is evaluate little f at the endpoints of the line segment. So all I have to do is take, so to do my line integral, note that this is just this. right? And so the fundamental theorem for line integrals says that this is just going to be f of 3, 4, my endpoint, minus f of 0, 0, my starting point. Um, 3, 4, plug it in. We get 9 halves minus 16 halves. That's the negative 7 halves. 0, 0, plug it in, you get 0. Look at that. That is fantastic because we never even had to parameterize the curve, right? We didn't have to do any of this. Now, this was a very simple curve, so doing it approach 1 didn't seem so bad. But if you have a really wiggly curve, like a really crazy curve, it can be very hard to parameterize. Not to mention, once you parameterize it and plug that formulation in here, it could be very messy. This avoids all of that. So this makes it very easy. We're just finding a function whose gradient happens to be the thing we started with. And if you can do that, you can't always do it. All right, it's not always going to be doable. If it's not a conservative vector field, can't do it. But if it is a conservative vector field, we can do that, and we can get our answer very easily. Okay, so that is fantastic. All right, I want to do another quick example. All right. Okay. This is going to look really hard at first, but then we'll see that it ain't so bad. All right, so let's do the integral of f dot dr, where f is the vector field, two xy minus 1, comma x squared, and c is shown below. Okay, we'll draw some axes here. And now I'm going to draw a picture of C. All right? Tried to draw as crazy a curve as I could. Right? That is C. I didn't even need to put the arrows on there because it doesn't matter how we parameterize this. But we got some crazy curve. Crazy, crazy curve. The hopes of parameterizing this thing, first of all, I didn't give you enough information. And secondly, even if I did, like the hopes of parameterizing this thing are you know, it's hopeless. It's hopeless. There's no way we're going to find a parameterization of this. That's a crazy, crazy curve. But we can still do this problem, right? If we can find, maybe we can find a potential function for this vector field. The potential function is the function whose gradient would be equal to this. So can we find that? All right? Can we find a little f whose gradient is capital F? Let's see. Well, I want the x derivative of little f to be 2xy minus 1. And I want the y derivative of little f to be x squared. Okay, well, if the x derivative is this, just anti-differentiate with respect to x. So that must mean that f is equal to x squared y minus x plus some function of y. We talked about this in the previous lecture, how if there was a function of y, this would still be an antiderivative of this, right? Because I'm differentiating with respect to x, so this stuff goes to 0. So you have to allow for that possibility, okay? There could be a function of y out here. And if we look at the second equation, I'm going to anti-differentiate this with respect to y. So that's just x squared y plus some function perhaps of x. Because when I differentiate this with respect to x, with respect to y, this is a constant. And so it doesn't matter. It could be there and I'd still get this. So I have to allow for that. And you can see that this will work. There is such an f, provided this guy is 0 and this guy is negative x. If that's the case, then these two things are the same. And so I found it. My function is just either read off the top line or read off the bottom line. You get the same thing, x squared y minus x. And you could, in fact, add any constant here. It would also work, right? So we found this function, x squared y minus x, satisfies gradient of f equals capital F. Now, why does that allow us to solve this problem, even though I have no idea what curve that is? Well, look at the curve. It's what they call a closed curve. Closed curves begin and end at the same point. So suppose this is the starting point. I could have picked any point, but suppose that's the starting point. AB. Well, it begins and ends at the same point, right? So that's also the ending point. Now, what does the fundamental theorem for line integrals say? Fundamental theorem for line integrals says that the integral along this curve of f dot dr is the same as, well, what we discovered was that f, we're not using the fundamental theorem yet, we just discovered that capital F is the gradient of this little f. Now we can use the theorem. The theorem is going to tell us that this is just little f at the end point, AB, minus little f at the beginning point, which is also AB. So I don't know what AB is, but I know that this is 0, right? So even though I don't know anything about that curve, I do, except that it's a closed curve, I know that my answer is going to be 0. And so this is a very important fact that we just learned, all right? If you have a conservative vector field and you do a line integral along a closed curve, you get 0. It doesn't matter what curve it is. If it's a conservative vector field, this is what's going to happen, right? So that's a very good, interesting fact that can allow you to solve some integrals very quickly, right? So if f is conservative and I shouldn't have a punctuation there, and C is a closed curve, then the integral of f dot dr is guaranteed to be 0. And that follows from this fundamental theorem for line integral. And this is one manifestation of conservation of energy. And this is one formulation of it, or one example of it, right? So if I was measuring the work done as I move along this curve, well, look, it's conserved, right? I get the net work is 0. If I started and ended at the same place, it doesn't matter where I went in between. The net amount of work done, work is energy, is 0. So the total amount of energy change was 0. The energy was conserved. And that's why they call it conservative. Right? This is really conservation of energy here. Okay, let me peek at the time. Okay, I think I'm just going to do one last example and then we'll call it. We'll talk about Green's theorem and then we'll call it quits. All right. So let me just take this off the paper and be a little friendlier here. Okay. So are there any questions so far? Nope. Okay. So the very last topic, all right, we're going to talk about Green's theorem. Green's theorem is another way to kind of view the fundamental theorem of calculus in this perspective involving vector fields. It's actually a special case of something else called Stokes' theorem, not the Stokes theorem. It's named after a guy, Stokes. Stokes, or Stoke. Stokes' theorem has as a special case Green's theorem and the divergence theorem. These things are discussed in your book. We're not going to get there, unfortunately. But if you want to read about them, they are there, and they're very interesting. They're very important. If you go on in engineering or physics, you're going to be using those. But Green's theorem is a special case, so we will at least get to see that. All right. So now that I just jumbled all my papers up, all my notes, where did I put it? Where'd you go, Green's theorem? Ah, here he is. Okay. Cool. So Green's theorem. All right. Here it is. I'm just going to come right into it and say what the theorem is. Suppose the vector field F is given by two functions, P and Q. Okay, so P is a function of X and Y, and Q is a function of X and Y, and that gives us a vector field. Okay. So it's just our X component and our Y component, and they each depend on X and Y. Green's theorem says the following thing. It says that a line integral along a closed curve. Now, to stress the fact that the curve is closed. Now, I haven't used this notation up till this point, although I could have, all right, but I was leaving it off so I didn't want to muck things up. If it's a closed curve, to emphasize that fact, we put a circle here on the integral. And that means that the curve begins and ends at the same point. Okay, so if it's a closed curve and we integrate, we do a line integral, that's the same thing as integrating over, what's D? D is the region inside the curve. Okay. It's the region enclosed by the curve. Let me I just want to peek at Green's theorem in the book. I want to make sure I wrote it down the same way they did it. Yeah, QX minus, good, they called it P and Q as well. Okay. We need to say a few other things about D, okay? D is not just any region, but it's what we call a simply connected region, okay? D must be a simply connected region. All right. What that means is that it can't have any holes in it. All right. So there's a mathematically precise way to define simply connected, and it has to do with loops. A simply connected region is a region where if you draw a loop inside, you can contract that loop to a point and stay inside of the region. And what that means is that the region can't have any holes, because if there was a hole and you put the loop around the hole, should come to, if you have the region and there's a hole in it, and you wrap the loop around the hole, you can't contract the loop to a point because you'll hit that hole and you'll have to stop. Right? I'm trying to see if I have something on my desk that, well, yeah, these scissors. So these scissors are not simply connected, right? Because if I were to put a loop if I drew a loop on this part of the scissors, there's no way I can contract that loop to a point, right? Because it gets stuck. The smallest that loop can get is right on the interior of this hole that I have in the handle here. And so these are not simply connected. Whereas if I take another object like, I don't know, like this coffee club card, you know, this is just, I draw a loop on this thing. Let's do this, do this side. If I draw a loop on this thing, I can contract that loop to a point, no problem. There's nothing that stands in the way. And so this is simply connected. So a simply connected region is a region that doesn't have any holes in it, essentially. Okay. So let's go back to the paper here. So let me just draw a picture down here. So you can have a crazy, crazy region. This is okay, right? But something that's not okay would be something that had a hole in it. This is not simply connected. This is simply connected. Okay, but so if you have a nice, you know, curve that doesn't have any, if you have a region that doesn't have any holes in it, so you can represent it as a single closed curve like this, then this theorem applies. Now, you might say, well, wait a minute, wasn't this equal to 0? Well, remember, that's not the case. If f is conservative, then yes. But if f is not conservative, then no. This does not have to be 0. It could be something else. Okay? So what I want to do is go back to the example that we did at the very beginning of class. And we're going to use this theorem to do it very, very quickly. All right? So it took us some time to do that example. Oh, I lost those notes again. Let me. So we were integrating around a. I have to find this. We were integrating around a rectangle. I hope it's not on the back of the thing I'm looking at. It almost is. There it is. We're integrating around this. We're doing this problem, right? We're integrating this vector field around this rectangle. Okay. Well, we did it by parametrizing the rectangle and doing the integral that way. And we got the answer. The answer was maybe you remember, -7/2. Right? Or no, that was that the problem? That was a different problem. Oh, it was, it's written right there. Oh, I'm such an idiot. Okay, I forgot I wrote it on the front page. I thought it was on the last page. Yeah, the answer was -3. Okay? So we did that, we got -3. Let's do this using Green's theorem. Okay, because this rectangle is a simply connected region, right? So what we know is that for that problem, we know that the integral around our curve is just the integral, a double integral over the rectangle, let's call it R, right, of qx minus py. Well, what was our vector field? Well, this is p and this is q. All right, so qx is 0, py is 2x. We're just taking the x derivative of q and subtracting the y derivative of p. So it's 0 minus 2x. So it's just -2x dA. And that rectangle is very easy to write down in this form, to find the bounds for. If I do this integral dx dy, well, x went from 0 to 1, and y went from -1 to 2. 0 to 1, -1 to 2. That should give us the answer, right? So let's see what we get here. So we get anti-differentiate the inside, -x squared. from 0 to 1. That guy is just -1. Find the antiderivative. It's -y. I'm going to evaluate that from -1 to 2. So that's -2 minus +1, -3. Look at how much quicker that was than we filled up over a page solving that problem when we did it by parameterizing the curve. We never had to parameterize the curve this time. So Green's theorem is amazingly powerful if you satisfy the assumptions. So it has to be a simply connected region. And then you can do the integral by doing the integral, a double integral over the area. So that's an amazing theorem. Very cool. All right. So, are there any questions? Nope, not seeing anything. Okay, so I guess we'll call it. We've covered everything I want to cover in the class. I mean, I wanted to cover divergence theorem and Stokes theorem, but I think given the situation, I think we'll just have to take things. We'll just do what we did the best with what we had. All right, so so I think that was pretty good. And so what we'll do is next week we will review. The final exam will be. We'll have to discuss next week. We'll have to discuss when we want the final to be. We can put it on any of our days. So we can do. Well, I want to give you 2 hours, so let's do it on any of our 2-hour days. So we can do it on. We meet. Yeah, we can do it Tuesday, Wednesday, Thursday. Well, we'll discuss. I forgot which days, how much we were supposed to meet on each day. So we could do it Tuesday, Wednesday, or Thursday. But I think one of those days we only meet for an hour, so not that day. So we can discuss when we'll do the final next week, and we can review problems. So please, when you come to class next week, think about things throughout the entire course that you might want to review, okay? Because we can review anything from day one. All right, any questions? Thursday would be the best. Yeah, what I was concerned about, I thought maybe everybody was putting their finals near the end of the week. But if Thursday's great, then I could totally do it Thursday. So if you have preferences, if you have a time restraint, something that's, you absolutely can't do it Wednesday or can't do it Thursday or something, let me know. And I want to take these things into consideration. We can talk more about this next week. Okay. So that's it. Okay, so see you next week, everybody.